Welcome. Let's start on this guy. So this is magnetic fields. So magnetic fields. So we're changing tack now. We've done electricity to a certain extent. We've done DC electricity. We've done electrostatics and all that kind of stuff. Now we're going to cut to magnetism. It might at first glance seem like it's got nothing to do with electricity, but it turns out it does. We can create magnetic fields by having circulating electric currents. And we do create magnetic fields, whether we like it or not. We are going to create magnetic fields. And sometimes that's a real bind, and sometimes that's wonderful. And then when we take that into account, we're going to start looking at inductors. These are magnetic components, where we want to deliberately magnetize and demagnetize bits of a circuit. They tend to be what's called a low-pass filter. So as the frequency gets higher, they are more resistive to the flow of a signal than they were at low frequencies. So capacitors kill you at low frequencies but let you go by at high frequencies. Inductors kill you at high frequencies but let you by at low frequencies. And then that leads us to where we end up, which is AC circuits, which is the classic thing is the tuning circuit. Which is used in radios and televisions and cell phones and all that kind of stuff. So that's where we go. We've got 4 chapters so far. We're going to have another 4 chapters, and then that will lead to basically electromagnetic waves, and then that leads us to light. So we go in this natural progression through the physical situation. So we'll start with just talking about magnetic fields. So magnetic field as the unit, as the symbol B. M's been used so many times. We have the magnetic field is B. Sometimes you will see H. It's a different thing, but we don't deal with H. So if you're looking through a textbook and you see H, it's related, but it's not the same. But we use B. And effect of B on a moving charge. So we have a magnetic field. Let's just fire an electron through it and see what happens. We find that it's a very complicated interaction. If I fire an electron through a capacitor gap, I know what's going to happen. It's going to be pulled by the electric field in one direction or the other. I know that. It's like gravitational field of Earth on a boulder. It will be the same as the electric field on a positive charge. It's very similar. Magnetic situation's very complicated. Not so complicated we can't understand it. It's just we've got to visualize better. And then we're going to actually use an application. And you actually do this as a lab. I don't know if you do it today. Probably not. You might. I can't remember. But it's the fine beam tube, which is used to measure the charge to mass ratio of an electron. Actually, it's a very famous experiment. Then we're going to do some comparisons between E and B, so we can compare and contrast. Remember what we say about critical thinking. If you've got 2 things, if you're comparing and contrasting them, you're probably thinking deeply about them. So we're going to compare and contrast. We're going to reintroduce the vector product. We did it with torque. We're going to need it again. And we're going to deal with basically a few things. And we're going to deal with current flowing through a wire in a magnetic field. We're going to deal with the torque on a wire current, a current currying loop. And we're going to talk about torque in terms of magnetic dipole. It turns out in all of this, there's about 3, maybe 4 cross-product equations that we need to know. And there's a pattern to them, so it turns out. Let's talk some conceptually about a magnet. Most people come across magnets as bar magnets. As a kid, how many people played with magnets as a kid? Yeah, that's actually not bad. Sometimes it's like next to nobody. Have you done the thing where you dangle it on a piece of string and it always points in the same direction? Did you do the thing where you got a cereal like cornflakes and ground it up so it became a powder and used the magnet to take the iron out of it? When they say fortified with iron, they mean fortified with iron. And you can take the you did the thing where two opposites repel. two opposite poles attract, two similar poles repel. And they're called north and south. And that's historical. They could have been called really anything. There is this issue where magnets tend to point in roughly the same direction on the Earth's surface because we have a magnetic field in the Earth. It's very important. It protects us actually from cosmic rays. It's called the magnetosphere. And it's caused by the rotation of the Earth's iron core. Very high temperature. When you get things really high temperature, they tend to be ionized. When you get a moving iron, you have a flow of current. When you have a flow of current, you create magnetism, basically. The Earth's magnetic field means that magnets tend to point in the same direction. It turns out when you fly in an aeroplane, they don't use that. They've not used that for years. The problem is if you fly over a region of the Earth which is great for mining iron, then you get a distorted magnetic field. It points in the wrong direction, so you'd end up flying around the magnetized region. Turns out, how many people here in Boy Scouts or Girl Scouts growing up? So did you do any map reading? Did you do about the angular deviation, basically? The North Pole moves. At the moment, it's in northern Canada. It will move around. It depends on... We've basically got this spinning liquid magnet inside. Well, electrical system inside. And that speeds up and slows down and reverses direction on geological time. And it changes its orientation in geological time. Well, actually less than that. So on the Ordnance Survey maps we had in England, it would say, here's the angle by which the North Pole is away from our grid north. So your compass will read wrong by 4 degrees in 1967, and for every extra 4 years, add on this many degrees. So you'd actually get the angle. So it's a very impure, untheoretical system. How do aeroplanes know where north is? How do they know where New York is?
Like GPS now.
So days probably GPS, but in bygone days they used to use a gyroscope, and they would they'd know the magnetic deviation where they were. So then they'd set their gyroscopes to point, so they'd go true north on their gyroscopes. And then as they fly, gyroscopes have this amazing property. They always point in the same direction unless you apply a real serious torque to them. So they turn the plane and the thing's still pointing north, and they turn the thing still pointing north, etc. Actually, I had this in class once. You're going to do a lab with magnetism, and your phone probably has a little magnet on it. And so we're doing this experiment with magnets where you use actually compass magnets to plot out the magnetic field. And one of my students very smartly said, oh, I'm going to use my phone for this, not realizing that it's not a magnet detector inside here. It's a GPS detector inside there. So it was like, and for a moment I was like, oh, that's interesting. Oh no, it's not going to work. Yeah, it's kind of interesting. So. SI units for magnetic field is the Tesla. Now, in truth, the Tesla is a huge unit. It's like, you got 5 of them, you got a really big magnet. I mean, really, really big. Traditionally, we worked in Gauss. Gauss, like the guy that did the electric field stuff. And a Tesla equals 10,000 Gauss. So it's like, the SI unit, though, is the Tesla. The equations work in Teslas.
How pompous do you have to be?
Pardon? I hope, yeah, okay.
To rename the unit.
The magnetic poles are designed for a designated north and south. They're just names. It just happens that we have a north in our maps and a south in our maps, and it's been there for, hundreds, if not thousands of years. Turns out that the North Pole of the Earth is in fact a South Pole. That's why it attracts the north of your compass to it. So it's a really weird situation, which can lead to a lot of confusion. Signal magnet as a pole. So you have this thing now. In reality, it's a magnetized piece of iron, basically. It might not need to be magnetized. It might have been deliberately magnetized. It might have been magnetized and dropped 4 or 5 times. So in reality, if you plot out the magnetism inside this thing, you'll probably get a North Pole which is strong around there, and you get a South Pole which is strong around there, but not necessarily the edges of it, because it's a real material made up of real domains of iron, and is there given more energy from the room temperature or been dropped, they tend to move to minimize their energy. If you think about it, if North Poles repel North Poles and South Poles repel South Poles, those 2 parallel magnet bits don't want to be next to each other. That wants to move away and that wants to move away. So you get this situation where you forever trying to get your magnets would by themselves would align themselves in your magnet draw like that, rather than like that. This is putting a lot of stress on the magnets because the North Poles don't want to be next to each other and the South Poles don't want to be next to each other. Well, inside the magnet, we have a whole bunch of little magnets. That's how it makes. There's a whole bunch of little magnetic domains, and the magnetic domains don't want to be pointing in the right direction. So the entropy, if you like, of the magnet says, I want to demagnetize myself. I want that domain there, and that domain there, and that domain there, and that domain there, and that domain there. And then every couple of weeks, we kind of remagnetize them and force them all pointing in the same direction. So then, as we point more and more of them in the same direction, we build up a magnetic effect which we can then begin to see externally by virtue of its effect on other magnetic systems. So that leads us to plot out our magnetic field lines. Or you might be doing this graph. Maybe you're doing this one today. And we plot them out, and they look beautiful. And they look like an apple core. Whenever I look at them from the side, I always look at them like an apple core. And if we imagine our earth bin our earth bin's like that. It's easy to see how near the North and South Pole we get a lot of magnetic field lines, but near the equator we don't get as many field lines. So the next thing I need to do is I need to say the SI unit for magnetic field is the Tesla. The magnetic poles are designated north and south. A single magnetic pole has never been isolated. It's like, how many of you actually cut up worms when you were kids? Ooh. Of course, Florida doesn't have so many worms. I'm from a clay region, and so there's worms all over the place. You dig in your garden, you get worms. And what happens is worms are horrible squishy things, and you go eek, and you get your spade and you cut them in 2, and you go eek, eek, because now there's 2 worms. And neither one of them likes you, because you cut them in 2. So it's this horrible nightmare where you chop them up and you have 100 worms. You can't chop them as much as that, but they do not. You can't have the front end of a worm without the back end of a worm. Well, actually, you can't have the front side of a piece of paper without the back side of a piece of paper. So why can't I have one pole of a north? Why can't I just have the north pole? Why just cut this in 2? Because what I'd find is I would have the north and the south, and I would have the north and the south.
What is the question? So if you cut them into half, the middle ones, so the south and the north from both ends, right there, it wouldn't be as strong as the outside ends, right?
If you separated these 2 guys, they would be as
equally
strong as each other. Yeah, there's nothing special about the north versus the south. So they'd be like in principle. Oh, so your sense is there's less material in each bit of the magnet. Yeah, probably. Yeah, I could live with that. Yeah, that makes sense. Otherwise, I could have just a row of atoms that are as strong as a whole line of atoms. And yeah, so that makes sense. Yeah, you're right. But let's go to this. So let's keep cutting and cutting and cutting and eventually end up with a row of atoms. Surely then I must have one pole or the other. Well, we realize that we have a row of atoms, but we still have a front face and a south and a back face. And you go, but front and back, that's just a relative thing. That's a name. It's a way of perceiving this. And so is North and South Pole. It's not a thing. It's a perception of it. I look at this row of atoms from this side, and I will see a North Pole. I look at the row of atoms from that side, and I will see a South Pole. If you like, imagine that these atoms are ducks. All the ducks have tails and heads. 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 If I look at these ducks from the front, I see a row of heads coming towards me. If I look at these from the back, I see a lot of tails going away from me. I don't turn around and say, oh man, the head and the tail are independent of each other. They're part of a dock. Yeah.
What's the force carrier for a magnetic field?
I think it's a photon, but I'm not 100% sure. Yeah, I'm not sure. So, what we say is magnetic field can be represented by magnetic field lines, just like electrostatic field lines can be. Magnetic field lines form continuous loops. They didn't in electrostatics. Well, hold on. They seem to be starting and ending here. That's because my diagram's not too great. Actually, these field lines go all the way through the material and back again. All the way through the material and back again. So it turns out they are continuous loops, whereas for electrostatics, they definitely started on the positive and ended on the negative. These are continuous. So that's kind of interesting. Magnetic field lines extend from a north pole to the south pole in the external field. Let me show you how you remember that. Point your finger. Point your finger. Okay? What's this bit called? Knuckle. There's your north. What's this bit called? You've got several of them. Point two fingers. What are they called? You said it? Tips. South Pole, knuckle. North Pole. Okay? We ignore K's in this. So, you point in the direction of your external field, north to south. You're going to do that an awful lot with your right hand. Any lefties? Oh, that's amazing. Okay, I've never had that before. Always use your right hand. We're going to do a whole bunch of right hand rules. And the magnetic field goes from the knuckles to the tips of your fingers, north to south. You point in the direction of the magnetic field. Speaking of right hand rules, let's learn some. So, I have a magnetic field. Now remember, we can have non-uniform magnetic fields and uniform magnetic fields, like we have non-uniform electric fields and uniform electric fields. Let's just take a uniform magnetic field. So there's my B. And imagine I put a positive charge in there. So, let's imagine it's this room. The magnetic field is going downwards. So, where is the north pole of my magnet? Is it above me or below me? The magnetic field's going downwards. So it's north is up. So north pole is up there, south pole is down there. I'm in the gap between. Magnetic field is going downwards. I'm a positively charged particle. I don't feel anything from this magnetic field. I don't even know it's there. It's not like an electrostatic field, not like a capacitor where immediately I feel that electric force. I don't feel anything. Okay, so magnetism has no effect on charged particles. but it does. Because I start moving, and depending on my velocity, I will feel an increasing force. So my effects, the force, the magnetic force, is velocity dependent. Depends on my charge, depends on the magnetic field, depends on my velocity. Well, that's weird. The faster you go, the bigger the force. That's weird. What makes it even weirder is it's to the side. It's at 90 degrees to my velocity. What happens when you have a force that's at 90 degrees to your velocity? We did this in Physics 1. What happens?
Goes in the circle.
My direction changes, I go in a circle. So not only does the force increase with velocity, I go in circles because of these forces. So very interesting. What I learned is that, and you can kind of see it, let's just, so it's going to depend upon my velocity. As my velocity gets bigger, my force gets bigger, so put V on top. It depends on the magnetic field. As my force gets bigger, as my magnetic field gets bigger, the force gets bigger. It depends on the charge. As the charge gets bigger, the force gets bigger. So it's going to depend upon Q, V, and B. So that makes sense. It's a vector. The force is a vector, so I'm taking a vector velocity and a vector magnetic field, and I am getting a vector answer. So that's raising the alarm bells of vector product or cross product. And so I can say, straight off the bat, F is equal to QV cross B. I want to teach you the right-hand rule. There's like 3 right-hand rules. There's several of them, and there's this one I want you to know. This is the one I would use. Because there's a right-hand rule that's like that, which works when things are at 90 degrees to each other, but we're rarely going to be at 90 degrees to each other. There's a right-hand rule like that, which is when you're at 90 degrees to each other, but rarely at 90 degrees to each other. And then there's this right-hand rule I want to teach you, which is based on the cross product. With a cross product, as I hope your teachers in Physics 1 taught you this. I hope I taught you this if I was teaching Physics 1 to you. You point in the direction of the first vector, and you twist your wrist or whatever until you can easily point in the direction of the second vector, and your thumb points in the direction of the answer. So in this case, my FB is given by, let's say that the velocity, let's say I'm traveling in this direction across the page, so I'm traveling this direction. And I have a magnetic field, and we said that magnetic field was going downwards. So basically I twist my wrist until I can just easily curl my fingers downwards. My thumb points towards the whiteboard.
So your thumb points towards the force, right?
The thumb is the answer, and the answer is FB. Yeah, for any cross product, the thumb is the answer. And in this case, the cross product says FB equals. So yeah, because we're going to use this over and over again. It's not just for this equation. So let's do another one. Let's say that your velocity is towards the towards the whiteboard, and let's say that your magnetic field points across the room towards the flag. Forces downwards. Agreed? Yep. The nice thing about let's do another one. The velocity is towards the periodic table. Let's say that the magnetic field is towards the left-hand edge of that screen. Yeah. Points downwards. The reason why I like this is because when it's 90 degrees, it's obvious, but sometimes it's only a little variation. The magnetic field is towards the red button. The velocity is towards the red button. The magnetic field is towards the little temperature controller. It's only a little variation. That won't work so well because they're kind of like not 90 degrees to each other. But that little curvy thing will work. So I prefer it. If you prefer the other right-hand rule, I'll teach you that one as well. But, you know, it means you've got to learn another one. And for this one, it goes like this. What's this called? What's that called? What's it called? A thumb motion. What's this? Magnetic field, north to south. So, do that. What's that? Pain. Caused by a force.
Forwards.
So with this one, you put your thumb in the direction of the motion, you do your fingers in the direction of the magnetic field, and your palm points in the direction of the magnetic force. Same kind of idea. That's all for positive charge. Negative charge, you get the opposite answer. So what I do is I just do it for a positive charge, and I say, what sign charge is this? It's negative. Oh, it's the opposite direction. It's the easiest way. You don't need another rule. Yeah.
So when you're doing, or when you're finding the direction of the force, so if you ask this for it, everything within a 90-degree window is going in the same direction?
No. What's
Or the
everything?
force, for example, if I was to use the right-hand rule
Oh,
for small,
you get the same direction of the answer.
right,
Yes, you do.
okay,
The only difference is the magnitude of the answer. So if I basically said, there's my velocity and my magnetic field is at 90 degrees to it, I'd get a big thumb up. If I did my velocities in that direction and I only go by 10 degrees, my thumb would not be as big. But it's the same direction. Yeah. Yeah. Yeah, it's just the size of it changes. Cool. So we say magnetic field vector, magnetic force vector, FB is equal to QV cross B. Consequently, the magnetic force is perpendicular to the plane containing the velocity vector and the magnetic field vector. Consequently, the magnetic field changes the particle's direction, because when you get force at 90 degrees to the direction of motion, you go into circular motion. The sign of the charge affects the direction of the magnetic force. We often want to know the direction of the magnetic force will act on a moving charged particle. We can use the right-hand rule, and we just did all that. Notice V cross B is not the same as B cross V. Opposite answer. So notice, what is this chapter about? Is this the chapter where we're introducing velocity, or is this the chapter where we're introducing magnetism? So it's about magnetism, isn't it, really? Magnetism comes at the back. Do you remember when we did talks? When we did talks, was that the chapter where we introduced radii? Or was that the chapter where we introduced, well, the forces? We introduced both, neither of them actually. But the force was at the back. Yeah, R cross F. The important bit, if in doubt, put the important bit at the back of the cross product. And more often than not, you'll be right. So it's going to be something cross B, and it's going to be other things cross B as we go through this. So here's a quick review of cross products. Basically, I have my vector A and my vector B, and if I point in the direction of A and then curl in the direction of B, my thumb points up in the red direction. So there's my answer. I went in that direction because I had A cross B. If I had B cross A, my answer would be downwards because it's in the opposite direction. So A cross B is not the same as B cross A. Actually, it's the same magnitude but the opposite direction. A cross B plus C is A cross B plus A cross C, so that's nice. It's distributive in addition. Now, for this one, if we write it out longhand, it's magnitude of A times magnitude of B times the sine of the angle between them, not the cosine. Sine for cross products. So if the A and B are parallel, then I get the sine of 0, which is 0. If I have A and B are perpendicular, I get my maximum effect. So for this kind of game, you get the maximum effect when you're at 90 degrees, just like with torques. And then there's this little bit, which I don't know if you remember this. or you can derive it, but we're going to use it in one derivation. The time differential of A cross B is A crossed with a dB by dt plus dA by dt crossed with B. We're going to use that. It's good to play with these things. So I crossed with I must be 0 because they're parallel, and J crossed with J must be 0 because they're parallel, and K crossed with K must be 0 because they're parallel. Now, because this is a cross product, I can't just say the answer's 1 when they both count. So I crossed with J. I crossed with J gives me an answer of 1K. It's positive Z direction. So I crossed with J is 1K. Positive, not negative K. Minus J crossed with I gives me the same answer, K. And you can do these others with the others. It's worthwhile playing with those so that you're comfortable with it. Change, they're interchangeable. A crossed with minus B is the same as minus A crossed with B. Just play with these things to prove it out. How do you do them? Well, the way I taught my class to do them is you do them with a little matrix thing, and you just cross multiply. So what you do is you want to know what the I term is, you put your hand over the I stuff and you cross multiply. And then you put a negative sign down. And then you put your hand over the J stuff and you cross multiply. And then you put a positive sign down and put your hand over the K stuff and you cross multiply. There's other ways. People extend the matrix. How many people were taught to just extend the matrix and do the cross determinant or something like that? Yeah, that works. If you do it that way, that's fine. I can figure that out as well. But the way I teach people was the way I was taught, which is the problem with my system is it only works really for a 2x3 system, whereas the other way I think works for more general systems. So let's do one. So what is the vector V cross B given by, notice, there's the old teacher mode coming out of me. What did I do to cunningly check you? What did I do? I gave you the B first. I'm just inviting you. Write this one down first and get it wrong. So, you got to say, let's call it something else. Let's call it J equals V cross B. And then you go I, J, K. And then you go, oh, what is my V? And my V is 2 minus 3 plus 3. And then what is my B? And my B is 3, 4 minus 2. Let's put some positive signs in here so that I know what I'm doing. And I can't show you this so easily with the system here, so I'm going to scribble a little bit. But what I say is that my answer, my J, is equal to, I put my finger over the 2 and the 3 on this side, and I cross multiply the others. So it's minus 3 times minus 2 minus 3 times minus, oh no, that's not right. Mistake number 1. Minus 3 times minus 2, 3 times 4. Put it in square brackets, and that's my I stuff. Then I put my negative sign down. Not most people, some people forget that. You've got to put the negative sign down. Then I put my finger over the middle bit, and I'm going to go 2 times minus 2 minus 3 times 3. That's J. And then I put my positive sign down. And I'm looking at these first 2 columns because I put my finger over the K column now. And so it's going to be 2 times 4 minus 3 times 3. Okay. And then I go, well, that's going to be 6 minus 12. I minus 4 minus 9 is minus 13J. And then 8 plus 9 is 17. Oh, did I just do those last two in one step? I just did those last two in one step. Sorry, because that's what I normally do it. Let me do it more completely. So then I go -4 minus 9 j, and then a plus sign, and I'm going to go 8 minus 9 k. Then I go in 6, that's minus 6i. -4 and minus 9 makes minus 13. There's a negative sign in front, making plus 13 j. And then an 8 minus minus 9 is plus 17 k. What's missing? Units. So it's going to be Tesla meters per second. Well, or what we know it as V cross B. Yeah, what we know is force. Well, actually, it's got to have a Q inside it. That would be newtons per coulomb, because I haven't multiplied it by the Q. But a small point, yeah. Put it in a box, and it's done. Any questions on that? Did I do it all right? I tend to miss this middle step because I'm practiced, but you know. Positive 5 coulomb charge carrier, positive charge, has a velocity of that speed through a region of uniform magnetic field given by that. What force does the carrier experience? I'm going to put us on pause. So we're back, and let's stop this and see how we're doing. So stop, and what do most people say? Most people are saying E, but not exclusively, so let's see how that goes. So with this, I think visualization is still important, although the tendency is sometimes for people to kind of not worry so much about the visualization. I think and the simple stuff, it doesn't matter so much, but in the complicated stuff, it matters. So I have a 5 positive, and then I have a velocity. So there's my V, and this equals 1I minus 2J plus 3K. And then I have my magnetic field, and my magnetic field is my B, and my B is given by 3I plus 1J minus 2K. This is going to be in Tesla, and this is going to be in meters per second. So then I go to my, I won't bother doing a list on this because I know it. It's going to be FB is equal to Q V cross B, and I'm checking, oh yeah, it's about magnetic field, so that comes at the end. So I'm just going to do my IJK over here, my IJK. And I put down my B, and I like to put down the B at the side to remind myself that that comes first. So I look across here, and I go 3, I go 1, and I go minus 2. And then I get my V. And did I do? Yeah, just. Yeah. But you noticed how I paused because I could just look and say, that's not, I just looked and said, that's not right. So it's V comes first. 1 minus 2 plus 3. I swear, if I'd not written down those things at the side, I would not have caught that. So then we have our B, and our B is 3, 1 minus 2. So then I put my finger over the I's, and I go plus 4 minus 3 is plus 1I. Minus, and then I'm going to put my finger over the middle ones, and I'm going to go minus 2 minus 9 is minus 11 J, and then put my positive sign. I put my finger over the last column. 1 minus minus 6 is plus 7 J. Okay, so that's V cross B. So I say FB is equal to Q, which is plus 5 times plus 1I plus 11J plus 7K. So FB is equal to 5I plus 55J plus 35K newtons. There you have it. So, as long as you know the equation, you can do the problem. Yes?
If the force isn't a vector, shouldn't you find the magnitude of the final answer?
Force is a vector.
Is it? But I mean, if it's just Newton's, I thought it had to have like a vector, you know.
It has got a vector. The IJK is the vector bit.
Okay.
The units are still the units.
Yeah. I mean, like, I thought the n would have to have the arrow to indicate it's a vector.
Oh no, because the n is the unit.
Oh, right.
I've never done it that way. It's just like it's just unit. It's that many newtons in this direction.
Yeah.
Yeah, cool. And then along came somebody, Fine. I don't know idea who it is. It's called Fine Beam Tube because it's a really narrow beam. They were playing with magnetism and they discovered that they could make magnetic fields using loops of current carrying wire. And a guy called Helmholtz had discovered that the geometry that gives you a very open, uniform field is a certain ratio of the two coils with a certain geometry. It's called a Helmholtz pair. So if you want to make a nice uniform magnetic field that's accessible, then you use a Helmholtz pair. That's what these orange bits are on the side. And then inside there's a glass tube filled with some inert gas like helium. And that's with a partial pressure that can be glowing light if you can excite it. So with a neon tube, you actually use an electric potential to cause the glowing neon lights, literally. The really remarkable thing is if I get a stream of electrons through a partial pressure of something like neon or helium or something like that, I can make those atoms that I collide with glow. What happens is the electron in the outer shell goes up a few energy levels and then comes back down and gives off a photon of that color. So I can make only those that I hit glow, and all the other ones I don't go near don't glow. So I can trace the path of my electrons. It's the most amazing thing. And then, because the electrons are in a magnetic field, they will go in a circle. So it's a way of visualizing, specifically visualizing the effects of a magnetic field on a moving charged particle. Now, I need to know something about the motion of the charged particle. I need to know its energy, and I get that from the design and the operation of the electron gun. Electron gun is basically a hairpin of glowing metal, usually tungsten. Electrons are emitted very easily from that. The electrons want to go in all directions. You use an electrostatic cup to confine them, sometimes called a Wiener cup. And then to accelerate them and make them go at the given velocity, you have an electrode, so it basically confines them and then accelerates them. Once they're accelerated, they coast around the circle. So there's an electron going in there. And you'll see this apparatus, probably next week actually, you see this apparatus. From a physics point of view, we say the magnetic force, there's a force due to magnetism that we need. And that's going to be QV cross B. Well, they're at 90 degrees to each other, so QV cross B simplifies to QVB sine, and they're at 90 degrees to each other, so it's 90 degrees, which simplifies to that. Okay, so it's the same expression, it's just simplified. And then we have our centripetal stuff I used to hate putting down. I'd say F is equal to M times A centripetal, which equals mv squared over r. Remember, I had this thing about I didn't like talking about centripetal forces, because the centripetal force is what you need to go in a circle. It's not what you get by going in a circle. So this force, this debt is paid for in this case by a magnetic force. I don't have a magnetic force and have a centripetal force. I've got a magnetic force, and it is required to be the same size as the centripetal mass times the mass times the centripetal acceleration. It's like you don't get holiday money because you go on holiday. You go on holiday if you have holiday money. So don't get the two of those confused. Centripetal force is a debt, it's not what you get. So put these two guys equal to the QV cross B. QVB is equal to mv squared over r. One of the v's kind of cancels, so the radius of this is equal to mv over qb. And we'll do that as a lab. Electron moves through a uniform 8 Tesla magnetic field at constant speed. So I'm going to put a particle here. It's got a constant speed. My magnetic field, let's have a look. Let's see if I can work this out. If it was a positive, my V would be that direction, and I'd want my force to be into the page. So my V would be like that. If it was a positive, I'd want my magnetic field to come out of the page towards me. Yeah? Point in terms of your velocity, curl towards your magnetic field to give you your thumb pointing downwards. But this is an electron. So rather than the magnetic field coming towards me, the magnetic field goes into the page. There's two ways I can show the direction of things that go into the page. This is going into the page, this is in, and that is out. Sometimes people forget the circle and put an X down. I don't like that. This is the recognized way. It's like an arrow that's got tail feathers on. 4 tail feathers. And when you look from this direction, you see the tip on the end, and you see the ring around the arrowhead. That's coming towards you, so that's coming out. And if you look from the rear end, all you see is that guy going away from you. So it's a really nice way of keeping track of that third dimension. You have the X, you have the Y, and you have the Z. It's a really nice way of doing it. So in this case, we said we want the force to be downwards. If it was a positive charge, it would be coming out towards me, but this is a negative charge, so I'm going to have that going into the page. So there's my B. I can draw as many of them as I like. Sometimes I draw 1, sometimes I draw 16. They're nice and uniformly spaced, as you can see. There's my B. And that B is equal to 8 Tesla. The path of the electron is perpendicular to the direction of the magnetic field. So it is. It's going across the page, whereas magnetic field is going into the page. The electron forms a circle of 5-meter radius. So this is 5 meters. So my R is equal to 5 meters. How fast was the electron moving? My V is equal to, I don't know. And I can't remember that equation. I don't need to remember that equation. I say FB is equal to Q, V cross B, which equals QVB, because we're at 90 degrees to each other. And F is equal to M times A centripetal, which equals M times V squared over R. So QVB is equal to MV squared over R. So what do I want to find? V. So V is equal to QB R over M. Took the R across, took the M across, divided by that. Yeah. So this is just sums. It's going to be 1.6 times 10 to the minus 19 coulombs. Let's have that as a negative because it's a negative charge on electron. Times B, which is 8, times R, which is 5. Oops. Times R, which is 5, over the M. And you don't know the mass of the thing, and I don't remember the mass of the thing. It's 9 times 10 to the minus 31 kilograms. So V is equal to, and what does it come out to be?
Where'd that V squared, how'd that V squared become V?
Because of that V there?
Oh, there's V almost, got it.
Yeah, yeah.
Got it.
So what's the answer? C. Shall I check it? How confident are you? Okay, so go 1.6 second EE to the minus 19, enter, times 8, enter, times 5, enter, divided by 9 second EE to the minus 31, enter. And I'm getting 7.11111 times 10 to the 12. C!
On our sheet, it says microteslas and millimeters.
Because I'm just messing with you. Okay, so I'm sorry. I improve things and I forget to carry them through the entire system, and I've got to improve that. Okay, electric and magnetic. Electric force acts in the direction of the electric field. That's pretty clear if we have an electric field. And I have a charge plus Q. Then my force is in that direction. That's my FE. Magnetic force acts perpendicular. There's my B. Here's my plus Q with a V. There's my FB. That's at 90 degrees. So that's different. Electric force acts on charged particles whether or not the particle is moving. Magnetic force acts on charged particle only when it's moving, and it gets bigger the faster that it moves. Electric force does work in displacing the charged particle when the force is in the same direction as your displacement work, because work equals the integral of fx dx. Remember that? Work equals force times displacement. In this case, your displacement is going to be perpendicular to the force. That's like carrying a bag across a courtyard. It might biologically tire you out, but your lifting force did no work. So that magnetic force does no work. So it's going to be a conserved force, whereas electric force is not conserved, magnetic force is conserved. So some interesting comparisons, contrasts and comparisons between these things. This is a great this is an interesting thing. If you can get hold of a couple of magnets and you get some silver foil and you just dangle the silver foil and you put the magnets on each side. I mean aluminum foil, I don't mean silver foil. And you basically get like a little power supply, a DC power supply, or even if you can get some batteries. Because there's not much, you're not trying to lift anything, you're just swaying something to one side. You can actually see this effect quite nicely. If I have charge carriers being pushed around when they move through a magnetic field, if I simply have those charge carriers inside a piece of wire, which is called a current, then as the charge carriers are pushed around, they'll push the atoms around, which pushes the wire around. So I can actually move a wire by passing a current through it inside a magnetic field. I'll do that later. So we have current carrying wire is a series of moving charges. It will be affected by magnetic field. So what do we see? Let's go through this. My current is the direction of positive charge, so my velocity in this third diagram is up the page. My velocity is up the page. Is my magnetic field pointing into the page or coming out of the page? All those X's say it's pointing in, so I point my fingers upwards, I curl my fingers into the page, and the force is to the left-hand side. And you see that wire flexing to the left-hand side. And then if I change the direction of my current, I push this thing to the right-hand side. And it is a real effect. Let's think about how much force we get for current flow. And we say, well, basically, let's take a certain length of wire. We know that for each individual charge carrier, we have FB is equal to QV cross B. And the V, of course, is your drift velocity. That's the net velocity on your charge carriers. So, okay. The force on the stream of moving charge carriers is going to be the force on each charge carrier multiplied by the number of charge carriers that are moving inside my volume, which is the number of charge carriers per unit volume, times the volume, which is the area, times the length of my piece of wire. So if I remember that my current is equal to the number of charge carriers per unit volume times the charge on the charge carrier times the velocity of the charge carriers times the area of the wire, then I get, oh, look at that. There's my N, and there's my Q, and there's my V, and there's my A. So I get, oh, the force, magnetic force on the wire is equal to I L cross B. Let's compare and contrast. FB equals Q V cross B. So it's a very similar equation, so don't get them confused. The format is the same. It's the important thing at the back. It's the thing that's affecting it, the length of wire versus the velocity. And it's something about charge. Charge in one case, current in the other at the front. Very similar equations. Let's do one. I'm going to do this one. A 3 meter length of wire lays in the positive x-axis. 6 amp, A6 Tesla magnetic field is given by, so let's just draw this in any old angle. This is B, and B is equal to 3I plus 4J minus 2K Tesla. 5 amps flows through the wire. Let's make it to the right. I equals 5 amps. What's the magnetic field? F is equal to QV cross B. That's not going to do it. It's the next one. Oh, yeah, I remember. F is equal to I L cross B. If I was kind, if I was professional, I would say what vector magnetic force acts in the wire, so there's no confusion that I want a vector out. I suppose I could say what magnetic force acts, and if you gave me a magnitude, I suppose I would have to accept it, but I really want to know, can you do the vector? That's of course a vector. So if I want to get the vector, well, let's be clear about this. This is equal to Q times the magnitude of L times the magnitude of B times the sine of the angle between them. And sorry, start. Oh, so it would be I, yeah, not Q. Yeah, it'd be I. So which way are you going to go? You're going to do this one way or the other. If I ask for vector, you'd know to go to this side and do the vector bit. But in either case, it's a lot easier to do the vector of my length and plug it in rather than try and find the magnitude and the angle between the two for my magnetic field. So I say, well, I know I is equal to 5 amps. I know that my L is equal to, it's going to be 3 meters in the positive x direction. Why positive x? Because I drew my current flowing in the positive direction. If I'd done my current flowing in the negative direction, it would be negative, that distance. It's the length in line with the current. So that then would be my good old friend plus 3I plus 0J plus 0K meters, and my B would equal 3I plus 4J minus 2K Tesla. I need to just look at this clock for a second. Ooh,